Good morning and welcome to this next lecture on vibrations of plates and shells. We are looking at forced response now, okay, and we have come up till here where we represent a displacement in the ith direction, I going from 1 to 3 as a weighted sum of the mode shape component, and this is the modal participation factor, okay, and its equation looks like eta k double dot, okay, plus lambda by rho h, okay, eta k dot plus omega square k eta k is equal to f k of t, which is the modal force, okay. And what does the modal force look like? Modal force looks like integral over alpha 1 alpha 2 q1 u1k plus q2 u2k plus q3 u3k a1 a2 d alpha 1 d alpha 2 divided by rho h n k. This will come up repeatedly. So, each of these is a function of alpha 1, alpha 2 and time. So, alpha 1, alpha 2 get integrated out, f k is a function of time, okay. Now, to put it in some familiar form, we say that lambda by rho h is twice xi k omega k. I think this is zeta, this is zeta, hold on, zeta, zeta k omega k, okay. So, this is a familiar form from 1D lumped vibrations, okay. So, which is where zeta k is called the modal damping coefficient, modal damping coefficient, okay. So, now eta k has to be solved for. The initial conditions have been figured out. So, how do we do that? How we do that is we take the Laplace transform route, Laplace transform. So, you should be familiar with Laplace transforms and seen them before in lumped vibrations, etc. So, that now if we take the Laplace transform of that modal participation factor equation, it looks like this: eta k of s, we have shortened the presentation, the Laplace transform of the modal force plus the initial condition that has this coefficient twice zeta k omega k plus the derivative initial condition, and in the denominator we have s plus zeta k omega k whole squared plus omega squared k 1 minus zeta k squared, okay. We are going to look at underdamped systems, okay, underdamped systems. And so, we will say that zeta k is much smaller than 1, okay. So, now if we invert this, which is quite easy to invert from tables. So, eta k of t becomes e to the power of minus zeta k omega k t, okay, eta k 0 cos gamma k t. Now this is the term which is gamma k squared, okay, and gamma k is the time natural frequency, okay, gamma k t plus eta k of 0, okay, gamma k is the damped natural frequency. Zeta k omega k plus eta k dot 0 sin gamma k t by gamma k. This is the homogeneous part due to initial conditions. Then we have the convolution integral due to the force, which is 0 to t fk of tau e to the power of minus zeta k omega k t minus tau sin gamma k t minus tau d tau. Okay. So this is the solution. Okay. Then we can have any u I alpha 1 alpha 2 t as summation over k eta k of t u I k alpha 1 alpha 2 is the total answer. Okay. The textbook now gives just a special case when the damping is 0, okay, zeta k is 0, then what do we get? The response is equal to eta k 0 cos omega k t plus eta k dot 0 sin omega k t by omega k plus 1 by omega k 0 to t f k of tau sin omega k t minus tau d tau. Okay, so that's the story of eta k. Okay. Now we have various systems. We have beams, okay, we have beams where we are, let us say, interested only in the transverse motion, and we have, let us say, plates, okay. We could be interested in the in-plane motion, rectangular plates in plane motion, okay. So A1, A2 are equal to 1, R1, R2 are equal to infinity, okay. So that means here the alpha 1 movement u1 and alpha 2 displacement u2 are uncoupled from alpha 3 movement u3. So there will be no u3 and u1 u2 equations. There is no u1 u2 in u3 equation, they are uncoupled, okay. So if such systems come up where u3 happens by itself, then fk will be 1 over rho h nk integral over alpha 1 alpha 2 as the case may be. If it is 1D, there will be only one integral, but if it's a general two dimensional surface Q3 forcing and the U3 mode shape A1, A2, d alpha 1, d alpha 2. And what is Nk? Nk will contain only the particular component U3, I am sorry, U3k squared A1, A2, d alpha 1, d alpha 2. Okay. And if it so happens that we are interested in the U1 displacement and the U2 displacement, and the forces are acting along U1 and U2 on the surface, that means there is a Q1 force, there is a Q2 force on the surface, then the Fk changes to 1 over rho h n k integral over alpha 1 alpha 2 Q1 U1 k plus Q2 U2 k A1 A2 d alpha 1 d alpha 2, and then Nk takes the form integral alpha 1 and alpha 2 U1 k square plus U2 k squared A1 A2 d alpha 1 d alpha 2. Okay. So that is how the Fk changes and Nk changes with the type of system and the choice of displacement that we want to look at. Okay. Now, a very important class of responses are steady state harmonic response. Steady state harmonic response. That means the forcing is a single frequency at 1 omega. So this is the time dependence term. So earlier the forcing was alpha 1, alpha 2 and time. So now it becomes Qi star alpha 1, alpha 2 e to the power of j omega t. Okay. As a result, what happens is the modal participation factor equation eta k double dot plus twice zeta k omega k eta k dot plus omega square k eta k becomes now, instead of fkt, an fk conjugate, which is a pure number e to the power j omega t. Okay. So now Fk star is just a number which is 1 over rho h n k, and it contains alpha 1, alpha 2 integrals of the spatial component of the forces Q1 alpha 1 alpha 2 star U1k alpha 1 alpha 2 plus Q2 star alpha 1 alpha 2 U2k alpha 1 alpha 2 plus Q3 star alpha 1 alpha 2 U3k alpha 1 alpha 2 close A1 A2 d alpha 1 d alpha 2. Okay. Now we can solve it now. What do? We say eta k, now eta k of t, right, is, I can write it as either a gamma k tilde, a complex number e to the power j omega t, or I write it as gamma k, a real number e to the power j omega t minus phi k. Okay, I can write it like that. Then what happens? If I substitute this back into this equation, okay, I get minus omega square gamma k tilde e to the power j omega t plus twice zeta k omega k j omega gamma k tilde e to the power j omega t plus omega square k gamma k tilde e to the power j omega t is equal to fk star e to the power of j omega t. E to the power j omega t goes, okay, and then gamma tilde is common, so gamma tilde k, and I get omega k square minus omega square plus j twice zeta k omega k omega. Okay, is equal to f k star. So that finally gamma k tilde is f k star by omega k omega square minus omega square plus j 2 zeta k omega k omega. One can leave it at this, no problem, because this can be substituted here and the answer is eta k. However, we can find the amplitude of this, which is amplitude of tilde k is f k star by square root of omega k square 1 minus omega by omega k whole squared plus 4 zeta k omega by omega k whole squared, and the phi k here, this phi k is tan inverse of twice zeta k omega by omega k by 1 minus omega by omega k whole square. Okay. So these are now for harmonically excited systems. Okay. Now what we are going to do is we have to take a few examples, right? We have to take a few examples and use this, find the force response. So the examples I will take on a large number are a simply supported plate, a simply supported plate. Okay, the method is same for any other, as long as you know the mode shape and resonance frequencies. Okay, so I have a simply supported plate, a rectangular plate, and it is simply supported on the edge all over. Okay. So now what do we have? We have the equation. Okay, so the equation now for a simply supported plate is A1 is equal to 1, A2 is equal to 1, R1 is equal to infinity, R2 is equal to infinity. If you do that, then the U3 equation gets decoupled, is decoupled from U1, U2 equations. U1 and U2 equations. Okay. So now what? Now if I write it in the way the textbook does it, okay, so I have minus EH cube by 12 1 minus mu squared into del 4 W by del x fourth. So let us say alpha 1 is x, alpha 2 is y, alpha 3 is z direction. So I get plus 2 del 4 W by del x square del y squared, okay, plus del 4 W by del y 4 minus, okay, lambda W dot minus rho h W double dot is equal to minus Q3 x comma y comma t. Okay, so now what do? We again do the same thing. My W, which is a function of x comma y comma t, I represent, okay, as, let me do it first, k going from 1 to infinity, eta k of t phi k x comma y. But we have seen the mode shapes of a simply supported plate, they have two indices. So in actuality it will be m going from 1 to infinity, n going from 1 to infinity. This will acquire the double index, this will also acquire the double index, and this is what? Sine m pi x by a sine n pi y by b. Okay. So now if I go ahead and substitute this form into this, if I go ahead do that, I get minus, I will replace this with d, okay. So I get a minus d double sum eta mn of t and m pi by a whole fourth plus twice m pi by a whole squared n pi by b whole squared plus n pi by b whole fourth, okay, into phi mn, okay, minus lambda eta mn dot phi mn minus rho h eta mn double dot phi mn is equal to minus q3x comma y comma t. Okay, or just once more, minus d sorry minus d will come only with this. Okay, so let me do that here, correct it here. Double sum minus d. Okay, d will come only with this term, whereas the double sum, let it go for all of them. Double sum goes for all of them. Okay, that's better. Okay, so now here let's see. Here I have the double sum with a minus. I get d eta mn m pi by a whole squared plus n pi by b whole squared into phi mn, okay, minus lambda eta mn dot, or let me keep phi mn outside here. Minus lambda eta mn dot minus rho h eta mn double dot, okay, into phi mn is equal to minus q3 x comma y comma t. Okay. So I've told you before that this part d into this part is rho h omega mn square. Okay, so I get minus double sum eta mn rho h omega square mn. The minus is outside, then these should be pluses. Minus is outside, these should be pluses, sorry. Okay, plus lambda eta mn dot plus rho h eta mn double dot into phi mn is equal to minus q3 x comma y comma t. And so now we multiply this by phi rs and integrate over the plate, let's say xy dx dy, and do the same on the right hand side, multiplied by phi rs dx dy and integrate over xy. Okay, then what do we get? We get, and I change the sign now. So I get rho h eta mn double dot plus lambda eta mn dot plus rho h eta mn omega square mn, okay, and we will call this nmn. Why? Because mn and rs are orthogonal unless m is equal to r, n equal to s. Okay. So now out of this sum, the mth and the nth indices are picked, so summation is gone. Okay, that is equal to integral over xy q3 phi mn dx dy. Okay. Okay, so this we will call let me divide by rho h. So I get eta mn double dot, and I will write it as twice zeta mn omega mn. Okay, eta mn dot plus eta mn omega square mn. Okay, is equal to 1 over rho h n mn integral xy q3 phi mn. Okay, so let's see one more time, let's do this. So what we have is eta mn double dot plus twice zeta mn omega mn eta mn dot plus omega square mn eta mn is equal to 1 over rho h n mn integral xy. I will do this here, q3 star xy phi mn xy e to the power j omega t dx dy. Okay, this we will write as f mn star e to the power j omega t, where f mn star is 1 over rho h n mn integral xy q3 star xy phi mn of xy dx dy. Okay, so this one may commit to memory for a while. Okay, why is that? Because now if I set eta mn to be equal to this my gamma mn tilde e to the power j omega t, okay, then my gamma mn tilde is equal to f mn star divided by omega square mn minus omega square plus j twice zeta mn omega mn omega. Okay, this double derivative here has resulted in minus omega square, that is minus omega square. This one derivative has resulted in the j. Okay, and this has positive sign that has resulted here. So what is the deal now? If we know q3, which is in terms of q3 star x comma y e to the power j omega t, the harmonic force, then I can know my f mn star. if I know Fmn star, I can know gamma Mn tilde. If I know gamma Mn tilde, I know eta Mn. Once I know eta Mn, the W x comma y comma t is the double sum Mn eta Mn of t phi Mn of x comma y. So Q3 Fmn star gamma tilde Mn eta Mn, that is the direction for steady state harmonic response. Okay, I did not specify steady state harmonic response. Okay, is where the initial condition effects or transients have died out. Okay, decayed away, and forced harmonic response remains. That steady state harmonic response. So that's important, okay, because it's some reasonable small damping. The initial or transients die away quite quickly. Then we are interested in this steady harmonic response. Okay, so that's the angle from Q3 to eta Mn. Once eta Mn is known, the response is known. Okay, so now for a rectangular plate simply supported in our example, we will look at the response of this simply supported rectangular plate for a number of systems, for a number of forcings, number of force types. Okay, we have run out of time. I will close the lecture here. We will continue from here next time. Thank you.